do negative probabilities exist in quantum mechanics? I'm guessing your answer is going to be no.
Yeah, it's not. Probabilities are always never negative in quantum mechanics. It's always either zero or positive.
What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a brilliant week and have a fantastic weekend in store. Now, today, we're going to be discussing the tricky issues of quantum mechanics and negative probabilities. You're probably all familiar with the idea that physical probabilities must take values between 0 and 1. However, famous historical physicists such as Paul Dirac and Richard Feynman have grappled with the concept of negative probabilities and how they could be used to potentially aid calculations in quantum mechanics and physics more widely. Over the last couple of weeks, Nassim Taleb, the famous Lebanese-American essayist, mathematical statistician and former trader, caused a little bit of a stir by seeming to suggest that quantum mechanics leans heavily on negative probabilities. Scientists pushed back, and Taleb responded in his usual belligerent style. One of the scientists who pushed back, Professor Nirmalya Kajuri, joins me today to help us all get to grips with the bizarre world of negative probabilities. Professor Kajuri is a theoretical physicist at the Indian Institute of Technology in Mandi, India. His research focuses on the interplay between quantum theory and gravity and the fields of ADS-CFT correspondence and quantum cosmology. Professor Kajuri is also a science writer and YouTuber and regularly produces fantastic threads illuminating fundamental physics on Twitter. His piece outlining the science contributions of J. Robert Oppenheimer is particularly noteworthy and worth your time. So who better to help us dive into the troubled waters of negative probabilities? Nirmalya, let's start from the start. Let's start with the human interest story. How did you get into this beef with Nassim Taleb, and what did he claim about negative probabilities and quantum mechanics?
Right. So I think it started with the video that you were showing on screen.
Yeah.
Someone tweeted this, and this came on my timeline.
How do I know if someone understands probability? They understand probability if they know that probability is not a product. It's a kernel. It's something that adds up to one, all right?
Mm-hmm.
So whatever is inside, okay, cannot be isolated. It's a kernel.
Okay.
You see, it is a thing that adds up to one. It's like saying the densities are not probabilities, but they work well within a kernel. We even had, at some point, people using negative probabilities. Just like in quantum mechanics, they use negative probabilities.
So when I saw this video, he was talking about probability distributions. I think at some point he said he was talking about negative probabilities.
Yeah.
And he mentioned kind of in passing that, some people invented negative probabilities. And he said, like in quantum mechanics, they use negative probabilities in quantum mechanics. So I was like, what? Because in quantum mechanics is a probabilistic theory.
Yeah.
But the probabilities there are always positive.
Yeah.
So what I thought was there is something in quantum mechanics called probability amplitudes.
Yeah.
Which can be negative. In fact, they can be complex. So I thought this was a confusion between probabilities and probability amplitudes.
Yeah.
And then I thought I would take this opportunity to do a bit of science communication.
Yeah.
So I retweeted this saying that no, we do not use negative probabilities in quantum mechanics,
Yeah.
and explaining what kind of probabilities we use and why they're always positive. And
so this idea of probability amplitude. So this is, if we're using rough kind of terminology, this is like the wave function, which describes a quantum mechanical system. But to get any measurable probability, any physical probability that we can measure, we need to take the square of this. And therefore,
that's exactly right.
In the end, we don't have negative probabilities. We have negative probability amplitudes, these wave functions that describe the system. But then when we want to get any observable out, we have to square them. So for anyone out there, you take a negative number, you take a positive number, you square it, positive. So he shouldn't really be suggesting that we have negative probabilities or that we rely on negative probabilities. It's not something we do in quantum mechanics.
Absolutely. So that I put that up. This was a Sunday, on a Sunday morning, and then I think in the evening, Taleb saw my post and he was not happy with it. So I think he made a post calling me a fraud,
Yeah.
and then my notifications were suddenly exploding.
Yeah.
His followers were trying to pile up on me, and then also a lot of bystanders, people were interested, asking about what if he meant this, what if he meant that, and what are negative probabilities. So it was a whole discussion. I was trying to reply to people, and then suddenly he came into my replies again, calling me like,
I think he used
that I'm
the
behaving like a
R
fraud.
word as well, didn't he, or something even worse? I
Yeah.
can't remember. Yeah.
He called me a fraudster and that I was being disgustingly dishonest, something like that. And so I responded with a GIF, which went like, "Daddy, chill." So I responded to chill about this. And then, and then it was over for like a week.
Yeah.
It ended for a week. And then next week, he again somehow, next Sunday evening, I don't know what happened, but
That
again,
must be
he
his like
replied.
designated Twitter aggression window on a Sunday evening. I'm bored on a Sunday. I'm gonna jump on.
Yeah. So then again, he was, calling me a new set of names, and he told me that, that I'm an idiot and and I was trying to bully him apparently,
Yeah.
and that I should repent and leave Twitter.
Very
To which I
mimic
just responded with a nah, not going to do any of that.
Yeah. So for anyone who's kind of followed Taleb kind of online, he's a statistician, he's an essayist, he's an author, he does a lot of probability based stuff. I think it's fair to say, and I don't want to get into a load of kind of back and forth personal stuff here. I want to use this as a chance for science communication, but I think it's fair to say that he has a very prickly attitude online. Like, he doesn't like being called out. I remember a particular situation where he was found to be following someone who was a bit of a Russian propagandist. Somebody called that out. He didn't like that. He goes very much on the attack when he feels defensive. So this is not, this is something that happens fairly frequently. I think people will realize with Nassim Taleb. Obviously, he has 1 million followers. He's a very famous person. So obviously, it drags in a lot of bystanders, a lot of fans of his. And then I imagine it's not much fun to be on the other side of that, right?
Well, I mean, it was kind of fun, to be honest, because I couldn't take this seriously at all. Someone shouting at you online from thousands of miles away is not remotely threatening. And of course, if you have 1 million followers, I think you should be a little bit responsible, because a lot of your followers could be quite unhinged. But even so, I mean, I was, it didn't bother me at all. I was happy to see some of my mutuals push back on Talib, such as yourself and others, kind of stand up to this. So that was, I appreciate that. But also at the same time, I couldn't take it seriously because there was no real engagement.
Yeah.
If he would, like him or his followers would engage with it or say like what he actually meant by negative probabilities quantum mechanics, then the discussion could move forward.
Yeah.
But all that was happening was he was posting a lot of papers which mentioned negative probabilities and quantum mechanics, but he clearly had not read those papers
but
because
not
they are not
understanding the
even
nuance
related
of
to each other.
So, and that's what we're gonna do today. Hopefully, we're gonna dive a little bit more deeply into it and understand kind of where these quote unquote negative probabilities where they potentially come in. But yeah, I think you're right, and I think there's a couple of things here. First of all, I'm glad it didn't affect you too badly. Like, I think I would have probably been a little bit more anxious about it, but I'm glad it didn't affect you too badly. And then on the other side of it, like you said, it is good that people push back on this, because I think there's a lot of stuff out there where when people just say the word quantum, it sounds smart. People think anything kind of goes in quantum because it's a probabilistic theory. You can kind of just, throw in a negative or throw in a complex number and it doesn't really matter. But there are rules here. It isn't just, you can't just throw in anything you like, and we have to be careful with the terminology we're using. So, okay, let's be charitable towards Mr. Taleb, whether he deserves it or not, and let's suggest that maybe he was talking about some of the ways we do use negative probability amplitudes in quantum mechanics. So let's jump onto the first proper science question then. So, do negative probabilities exist in quantum mechanics? I'm guessing your answer is going to be no.
Yeah, it's not. Probabilities are always never negative in quantum mechanics. It's always either zero or positive.
Yeah.
So quantum mechanics is a theory which predicts probabilities. And as you are showing on the screen here, this is the wave function or a probability amplitude. And we always have to take the square of it, and the square is guaranteed to be positive. So let me give one example. The simplest example of a quantum mechanical system is one with a spin. So it can be either in a spin up state or in a spin down state. And when we are not observing the system, it will be in some kind of combination of spin up and spin down. So it will be some complex number A multiplied by a spin up state plus B multiplied by a spin down state. And the probability of observing it when we do the measurement in the spin up state is A squared, modulus of A squared. And on the spin down state is modulus of B squared. So these squares are the things that we can observe, the probabilities, and these are always guaranteed to be positive. Now we can talk about more complicated quantum systems, more complicated, using more sophisticated maths of Hilbert spaces and projection valid measures and so on. But the key point is the same, that it's always guaranteed to be positive squared probabilities. Probabilities are always positive.
So those numbers that are in front of the states, those A's and B's, they can be complex numbers, they could be negative numbers, but eventually we're going to have to square them out, or we're going to have to take the complex conjugate with the original, and therefore we're going to get a positive number out in the end. We have to get a positive probability out. We have to, otherwise we're not going to be able to observe everything. And quantum mechanics is a theory that predicts observables and probabilities of those observables. So we can have these funky descriptions of the wave function, but eventually when we want to make an observation, they're going to get squared and we're going to get positive numbers.
Absolutely. It's possible that there could be a future theory or future modification of quantum mechanics which allows for, in some way, negative probabilities, whatever that may be. But the current quantum mechanics that we have that explains all our observations of nature does not allow, it's inbuilt that the probabilities are positive.
So why do you think people fall for this mistaken idea that quantum mechanics is awash with kind of negative probabilities? Is it this idea of that we have to square things? So people see, for example, images. I've got some here. So this is a very common question, by the way, on physics. If you go to physics notice boards, you see people talking about, do we have negative probabilities in quantum mechanics? Do we need them? Where do you think this comes from? Is this because people look at those wave functions, they look at those probability amplitudes, they see these kind of negative numbers, sines and cosines coming in, and then they just think, oh, okay, I know that's related to the probability, so yeah, there's some negative probabilities here. Is that where this is coming from, do you think?
I think so. I think, we talk about probability amplitudes in quantum mechanics. So quantum mechanics tells us, the final result, as you were saying, is probability. But in all the intermediate steps, we calculate the probability amplitudes or the wave function. And this thing is a complex number. It can be negative, it can be imaginary. It's a complex number. And one of the famous thought experiments in quantum mechanics, for example, is the double slit experiment, where you have a source of, say, electrons, and you have a barrier with two closely spaced slits. And then you look at, this is the picture. Then you look at the screen, and the screen you get this alternate spots of light and dark spots, which is an interference pattern. Now, why are we getting an interference pattern? Because the way we calculate this is we calculate the probability amplitude of a particle going through one of the slits and then ending up at the screen, plus the probability amplitude of the particle going through another screen and ending up at the screen. So we have to add this probability amplitudes and then take it square. And so when we add them, these are complex numbers, so they can be out of phase, so they can cancel each other.
So they can add to zero and we get one of these dark spots, or they can add to double and we get one of these. We get the central maximum. But we have to deal with these probability amplitudes, add them, and then in the end square everything up, because you can see here there's no negative light. That doesn't make any sense.
Yes, exactly. So there's no negative in the picture. It doesn't make sense. But if people were reading about this in a popular science thing, and all they know is that quantum mechanics deals with probabilities, they might think that we are adding the probability of the particle going through this slit and coming here, and the probability, and those probabilities are canceling out. And if there's a probabilities are canceling out, then one of them has to be negative.
Yeah, of course.
I think this gives the impression that maybe probabilities can be negative, whereas what we deal with actually are the probability amplitudes.
Yeah. And these amplitudes, so just a nice little picture here. So we have these wave functions here. I'm not sure exactly what system these represent. I don't think they represent any particular system, but you have the wave function, which is describing your system. For example, these might explain the probability of finding the particle at a particular value in X. And the wave function that describes the system can be negative, can be complex. But once we want to find out the probability of the particle actually being somewhere, we want to make an observation, a probability of making a particular observation, we square that up, and this negative becomes a positive, this negative part becomes positive. And all of the values, all of the observables are going to be, and the probabilities of those observables are going to be positive, as you say. So I really do think this is where most of the confusion comes, in the dealing between probability amplitudes, these wave functions describing the system, and then that you have to square these up to make anything observable, anything that you can look at. In fact, I think if you go back to the video of Taleb speaking, he was talking about bits and pieces inside integrals, and I think he was getting himself a little bit confused between these probability amplitudes and probabilities. I think if you're wanting to give a kind of generous reading of what he was saying, I think that's where the confusion was. He's obviously not a physicist, and he was quite aggressive about people pushing back on this. So there are some places as well in quantum mechanics, in quantum field theory, where negative probabilities come up, right? So other places where you see this kind of thing are in the Dirac equation and the history behind the Dirac equation. So there's also famous physicists who have grappled with these ideas, right? And maybe this is another place where it gets into the popular culture that these things are all over the place in quantum mechanics.
Right. So what happened was that in the early days, when people were trying to combine special relativity with quantum mechanics, at that time, people had this equation, which is Schrödinger equation, which is the older equation for quantum mechanics, which does not have relativity incorporated in it. And then people were trying to upgrade this equation to get a relativistic equation for the wave function. And then people came up with this equation, which is on the screen, the Klein-Gordon equation. And then people initially thought that this was the equation for psi is the wave function, and it tells you how the wave function changes with time. And with this interpretation, people then ran into two problems. One was they said negative energy solutions, and the other was it was giving negative probability density. So at that time, people were grappling with what is this negative probabilities and how to make sense of this. Eventually, we now know that was a wrong interpretation. That the psi that appears here is not the wave function. This is not the equation of the evolution of the wave function. This is the equation of a field. We now know that we have to describe the universe using fields. And so this is a field which has not yet been quantized at all. This is a classical field which describes spin zero, a spin zero system, a scalar field. And when we quantize this field, we get particles. So the excitations on these fields are the particles. And when we do it like that, there are no negative probabilities. All the probabilities that come up are positive. And we understand these are spin zero particles. So it's like Higgs boson is an example of a spin zero particle.
So in this situation, people took the Schrödinger equation, which is not relativistic, and they said, okay, well, I really want to turn relativity, I want to merge relativity and quantum mechanics. And the way I know how to do that is, well, I have this relativistic energy equation, and I have my operators that represent quantum mechanical variables, and I'm just going to mash those together in the very simplest way that I can. And then the problem with that is it was predicting that you get these negative energies and negative particle densities, essentially negative probabilities were coming out of this system. And we now know the reason for that was because we were describing things wrongly. We were describing them as single particles, and we should have been describing them as fields. However, the interesting thing off the back of this is that Dirac obviously realized that these were a problem, and therefore he went and developed a different way of dealing with these, which was the Dirac equation. So the fact that physicists saw negative probabilities in the mathematics of their theories, told them that there was something going wrong and that they had to formulate things in a different way. So rather than quantum mechanics relying on these things, it was a feature of the mathematics, a kind of bug, if you will, in the mathematics that physicists realized they had to work around, and actually gave a lot of forward motion in the field because people realized that these couldn't stand. In fact, I think I've got a really nice, I think there's if I find here we go. So Dirac actually did, can I find the talk that he did? I'm sure I had it. Yes, he did a Beckerian lecture in 1941. And I just want to take a little quote from that. So the thing that people quote about negative probabilities, or at least did in your thread, they quote Dirac saying negative energies and probabilities should not be considered as nonsense. They are well-defined concepts mathematically, like a negative sum of money. And then they stop there. And they say, oh, look, Dirac, thought these things were important. He knew these things were important. Yes, he knew that they were important from the point of view of the mathematics, but he knew that they couldn't be physical. So if you carry on reading this, he says, since the equations which express the important properties of energy and probability can still be used when they are negative, thus negative energies and probabilities should be considered simply as things which do not appear in experimental results. So essentially what he's saying is, you can use these things mathematically, you can still use the mathematical system, but you have to be aware that they can't give physical results, which is exactly what you've been saying all along. So Dirac having a lecture where he says these things are important is not necessarily saying what people think he's saying. He's saying, yes, the mathematics says this, and yes, that's consistent in the mathematics, and yes, maybe we can use this mathematics to give insight, but the way that we kind of deal with that insight, we have to understand very carefully that in the end, these probabilities have to be positive.
Yeah, exactly. So so people were quoting like the first line of this and saying, Dirac said this, obviously, who are you to question Dirac?
Yeah, and then people go like, you think you're smarter than Dirac? It's like, no, I just read the next line of the paper and I completely agree with Dirac, but you don't actually. So yeah, and it gets very fraught very quickly. So I just thought this was a really interesting case where physicists realizing that the mathematics that undergirded something, an attempt to understand quantum mechanics and relativity, the failure of the mathematics there actually led them to do something in a different way, which pushed forward our understanding of the universe. Because when Dirac came up with his equation, he very quickly realized that this was now an equation that described spin-a-half particles, fermions, rather than the spin zero particles that you were talking about. So we now had a new equation, a new formulation of relativity and quantum mechanics that allowed us to deal with spin-a-half particles. And obviously, if we're talking about the standard model, where everything is spin-a-half particles, more or less, then this was incredibly important. So I think people need to be a little bit more nuanced when they talk about how important Dirac thought these things were. Is that fair?
Yep, I agree. Yeah. So Dirac obviously had that problem with negative probabilities and negative energies. And then he came up with a new way of combining relativity and quantum mechanics, as I said. That's the Dirac equation. And it still had the problem of negative energy particles, but then it was solved. We know that's an electron and a positron. So this equation gives us both electron and its antiparticle positron. So a lot of things moved forward because people realized that there was a problem with negative probabilities and negative energies.
It's quite interesting, actually, because the two people that they talked to, that we're going to talk about Richard Feynman later, the two people who solved the negatives in that problem. So first of all, Dirac solved the negative probability densities, like you said, and then it came to Feynman and Stockelberg to reinterpret the negative energies in there with, as you say, a particle and an antiparticle. So it brings those two brilliant physicists together. And I think when you see Dirac and Feynman talking about negative energies, negative probabilities, people just see that and think, oh, well, it must be a real thing because these brilliant people were talking about it. But there's a little bit more nuance, a little bit more interpretation that needs to go into that. Okay, so we've discussed a couple of reasons why maybe people think quantum mechanics is awash with negative probabilities. I want to talk about a few more things that people talked about in the thread as well. So Taleb fans kind of push back on this idea that quantum mechanics doesn't rely on negative probabilities. And they point to a few different examples that look like quantum mechanics relying on negative probabilities. So they point to the Wigner pseudo probability distribution, the use of ghosts in quantum field theory, and a paper by Richard Feynman on the topic. So I'd like to discuss those, and let's start with these this Wigner pseudo probability distribution. So maybe if I bring the paper up on that. A distribution that's used in quantum mechanics and which can dip into the negative. So what is the Wigner pseudo probability distribution, and why does it not represent using negative probabilities in quantum mechanics as Taleb suggested? Why is this not his his win here?
Right. So in classical mechanics, we know that we can for any particle, we can describe it by its position and momentum.
Yeah.
We can simultaneously know the position and momentum of a particle. But suppose instead of having one particle, we're dealing with like a box of gas molecules, a lot of particles. And then it's not useful or even possible to track the positions and momentums of all those particles.
Yeah.
So what we would like to know is the average position and average momentum of this collection of molecules. And then that is given by this kind of formula where you have some probability distribution F of a particle having a certain position and a certain momentum. So the probability of particle being here and having a certain momentum is given by F of QP. And then when you do this kind of integration over it, you get the average position and average momentum.
So here at the moment, we're dealing with classical mechanics where we're saying, what's the probability that a particle is in this section of the box and is traveling with this velocity, for example? We can integrate over the system, and we can get some average values for position and some average values for the momentum in the box, depending on temperature or whatever it might be.
Yeah. And so this is very useful to work with. And this position and momentum together is known as phase space. So these are called phase space probabilities because it's a probability in phase space, which just means position and momentum. And so now Wigner wanted to figure out if there could be something like this in quantum mechanics. The issue in quantum mechanics is that we have now an uncertainty principle, which prohibits us from knowing the position and momentum of a particle at the same time.
Yeah.
So obviously, it was not going to be possible to get a probability of finding a position and momentum because you cannot have that.
Yeah.
However, Wigner found this distribution, this formula, which is given by this WQP that you are showing here.
Yeah.
And this rho here is something called a density matrix. Anyway, but this thing, the interesting thing about this W, which is now called Wigner function, is that it has a lot of similarities with the classical probability density. And the similarity is that if you add it up, if you integrate it over Q and P, you get 1. So it adds up to 1, like a probability.
Yeah.
And it also gives us the expectation values of the position and momentum when you integrate over them, exactly like the previous formula.
Yeah.
So this Wigner function is a very interesting and useful object in quantum mechanics, particularly for people who work in quantum optics, quantum information. However, it also can have negative values. So it can dip below 0. And this is not exactly a probability.
So this is, it can, even when you integrate up, it can give a negative value, not just, so you integrate this up, it can give negative, I don't think it can give negative probabilities though, right?
No. So when this W itself can have negative values.
Yeah.
When you do the integration with Q, it will give the expectation value of Q, exactly like quantum mechanics does, and similar for P. So position and momentum expectation values will come out to be positive.
Yeah.
Do the integration. And so the reason we don't call them probability is, first of all, we know how to compute probabilities in quantum mechanics. That's a different thing. And in fact, you can compute the probabilities from the Wigner function. If you were to take the Wigner function and you integrate it over momentum, for example, you would exactly get psi q square, which is the probability amplitude square, the wave function square.
Yeah.
So from the Wigner function, you can actually recover the probability which is always positive.
Yeah.
Secondly, probability has this property, which is that if I have two mutually exclusive events, then the total probability of these two mutually exclusive events always add up.
Yeah.
So, for example, if I'm throwing a dice,
Yeah.
I have the probability of getting 1 is 1/6, the probability of getting 2 is 1/6, but the probability of getting either 1 or 2 is the sum of 1/6 and 1/6, which is 1/3.
Yeah.
So that way, probability of mutually exclusive events always have to be added.
Yeah.
And wigner functions don't have that property.
Right.
So that's why these are called quasi-probabilities.
Yeah.
So mathematicians have developed a theory of probabilities, like an axiomatic theory of probabilities, using just 3 properties of probabilities, which is that they're always positive, they add up to 1, and mutually exclusive probabilities add up.
And the wigner function breaks one of those axioms. It doesn't.
Wigner function breaks one of those axioms. So these are called, I think, Kolmogorov axioms in mathematical theory of probability, and the wigner function doesn't satisfy them, and hence they're called quasi-probabilities.
Yeah.
But this is semantics. The key takeaway about wigner function should be that they're very useful quantities, and when they dip into the negative, it kind of gives us some information about the quantum nature of the system, because it's a departure from the classicality.
Yeah.
So these are very interesting things to look at to understand when a system is departing from its quantum behavior and things like that.
So again, this is essentially interesting behavior that is going on in the mathematics that describes the system, but it's never going to be able to produce a probability which is negative in the end for an observation. So we might be able to look at the fact that it dips into the negative and say, okay, something odd is going on there. There's some weird interference effect happening. We might be able to get some insight into the system from it. But in the end, any probability that comes out of it is still going to be positive. The probability of getting any observable is still going to be positive. So again, we're not, and there is a little bit of semantics going on here, but we're not relying on negative probabilities. There are no negative probabilities in the end.
Exactly.
So it's, again, a useful tool. There are negatives in the mathematics, but by the end, when we get to the end of the road, they become positive again. Excellent. Another thing that people were pointing to and saying, well, is this not the use of negative probabilities in quantum mechanics was ghosts. Now, I will admit that this is a little bit above my pay grade. This meme probably describes it quite well. What are these ghosts? So I've heard a little bit of talk about, is it Faddeev Popov ghosts in quantum field theory and these kind of things? What are these ghosts, and why are people potentially pointing to them as the use of negative probabilities in quantum mechanics?
Yeah, that's a good question. Okay, so these ghosts appear when we are trying to quantize gauge theories. So let me first talk a little bit about gauge theories. So when we are, when we have, because we have theories which have the symmetry of relativity inbuilt into them. And relativity is a symmetry that basically says if you go from a moving frame to if you're in a moving frame or if you are in a rest frame, you cannot tell the difference, whether you're moving or not moving at a constant velocity. And that's a symmetry. And so when we do the calculations of the theory, it's often useful to do it in a language which makes the symmetry apparent at every step. And that makes life a lot easier when you know that the symmetry is there, and then you're not making a mistake.
Yeah.
Because you have the symmetry at every step.
Yeah.
Now there are certain theories which don't naturally take to this language. So if you want to put them in a language where you can have the symmetry apparent at every step, you have to introduce some extra variables.
Right.
So there is some kind of a redundancy of description in these theories because of these extra variables. And these theories are called gauge theories. So let me give one example of this, which is electrodynamics. So when we do electrodynamics using potentials instead of fields, it's a gauge. It becomes a gauge theory in the sense that there is some redundancy in description.
Yeah.
If someone has taken a high school physics, they will understand the example that I'm going to give now. The simplest possible example is take the electric potential. And the electric potential, the derivative of the electric potential is the electric field.
Yeah.
which means that if you add some constant to the electric potential,
and then it gets
it's
and
the same
then when you
electric.
do derivation, it goes away.
It goes away. So the potential, one potential V and the other potential V plus some constant describe the same physical field.
Yeah.
So there is redundancy here.
Yeah.
And this is the simplest example of gauge theory and of gauge freedom. And when we do this, more sophisticated things are just this with more bells and whistles. So now when we try to quantize this gauge theories, it has to be done in 2 steps. So first we quantize without caring about the redundancies or the extra variables. We just take it and make it a quantum theory where we have those states, we have vectors and so on. And then we find that we get some states which have negative norm or negative magnitude. So that looks like negative probabilities. But these states are not physical states because we just took all the redundancies and then quantized. We have not yet gotten rid of the redundancies. So to do that, we have to impose something called the gauge condition. And when we do that, we are left with physical states. And the reason they're called physical states is because they represent the physics of what is actually going on.
Okay, so
And
again, this is something, and this seems to be a recurring theme of this discussion, is that these are things that come up in the mathematics working towards the final probabilities, the final states. But once you get to the final states, they've disappeared. So they're useful in the description of the system and the mathematical modeling of the system, but by the end they've disappeared. So you kind of don't rely on them. You just kind of use them in an intermediate step.
Exactly. So if you want to do the quantization where you want to make all the steps symmetric, as I said, keep the symmetry apparent in every step, then you use this way of doing it where you get ghosts in the intermediate steps and finally you get rid of the ghost and get all the physical steps. And you could also have done this quantization in a different way where you impose the gauge condition first and then quantize, and that you would never see those ghosts.
You would never see the ghost. Right, okay. So it's two different mathematical ways of doing something, but they result in the same end final state with positive probabilities. Okay. Yeah.
And in one of those ways, you get some ghosts in the intermediate steps, some negative probability states in the intermediate stages, which are not there in the final formula, final theory.
I see. So this is coming up again and again and again, that you can rely, or you can take advantage of the idea that there's kind of these negative probability states in intermediate steps. Yeah. But by the time you get to anything that describes the physics underlying the universe, they've disappeared. So they're at best a kind of a tool, a kind of thought experiment and a way of doing things. Very, very interesting. Now, of course, people go beyond that. And the other big thing that they point to, I think you sent me a quote as well that might help.
Yeah.
Just as we come to the end of this section on ghosts.
Yeah. So this is from David Tong's lecture notes on quantum field theory, and he's talking about ghosts, and he says, look, this negative sign over here in this equation looks like negative probabilities, which makes no sense at all. But then he says, at this point in the next paragraph, that we have not imposed a certain equation on the theory, and this is going to come to our rescue. So that when we impose this equation, it's going to get rid of this ghost states and leave us with positive probability states.
Right. So again, this is a situation where the mathematics that we've used to get to the final answers has some of these intricacies, some can produce some of these strange looking things, but then you have to apply other conditions on the system that actually give you back the real physics underlying the universe. So, okay, there's an example of that in play. Right. So another thing people were pointing to in the thread that you had is obviously Richard Feynman talking about negative probabilities. This is basically, if you Google negative probabilities, this is the first thing that comes up, which is a paper by Richard Feynman, and I think it's from the 1970s, if I am correct. So
it's 1984.
Yes. So let's discuss this paper. What was Richard Feynman exploring, and why does this paper not suggest that negative probabilities are routinely used in quantum mechanics? Because it literally says at the top Negative probability in big bold letters. So what's going on here? Why is this paper not Taleb's win? Because I think when you pushed back on him and told him that all probabilities are positive in quantum mechanics and lots of physicists agreed with you, this was kind of what he threw in your face while calling you a fraud. Was this paper off his Google? So what's going on here?
So yeah, before I address that, let me just say that this is not how you argue in physics. You don't argue by referring to an authority figure. This is a fallacy where you don't say Einstein said this, that's why this is true. Yeah, you have to give an argument as to why this is true. Anyway, so let's come to this paper.
Totally agreed. Good.
Yeah, coming to this paper, I had actually not seen this paper before.
Neither had I. I'd never heard of it. Which probably tells you something, right? That two trained physicists have never heard about this paper. Probably tells you how far it got within the mathematical formalism of quantum.
How secret people have been keeping the negative probabilities in quantum mechanics.
Exactly, we've been keeping it very, very secret and using it in secret for many, many years.
So this paper is kind of Feynman, thinking out loud, is speculating about, what if there are negative probabilities? This is not a review of negative probabilities in quantum mechanics. This is not a discovery of negative probabilities in mechanics. I think this was someone's birthday conference, and he took this occasion to think out loud speculate about how if negative probabilities can arise in physics, and if my theory gives negative probabilities, if someone comes up with a theory which predicts negative probabilities, how should we understand it?
Yeah.
And how should we, deal with this? And then Feynman concludes that there could be, probabilities arising in some intermediate steps, which could be negative, as we have been discussing all along, that there could be negative probabilities in some intermediate steps, which go away in the final step.
Yeah.
So that's basically the observation of this paper. It's a fun paper. And he gives one example, for example, of some roulette table. But suppose if the table is in some, so the table could be in two different states, A and B, and there's probability of the table being in some state A, and there's some probability of the table being in some state B. And when they're in these states, there is some outcome, which we are finally observing. And there's some probability of these different outcomes. And so his argument is that suppose one of the probability of the table being in some state is negative. We would never observe that probability in the final result. So it is some intermediate probability that could be negative. And he's saying that, if the intermediate probability is negative, but it doesn't show in the final result, there's no contradiction with experiments. Yeah. So maybe an intermediate probability could be negative, and maybe in the future we have some theory which gives negative probabilities. So don't, throw away those theories. Try to interpret them. That's all he's saying.
Yeah.
He's not talking about any existing theory having negative probabilities.
Yeah, he gives a very simple. So just to talk about, he talks about, and this is again the one line that people take away from the paper. So he says, I think I've got the quotes up here. So he says, where are we? It is usual to suppose that since the probabilities of events must be positive, a theory which gives negative numbers for such quantities must be absurd. I would show here how negative probabilities might be interpreted. Like you said, he just wants to talk about the interpretation of these. And then he gives the example of basically negative apples or negative money. So somebody could have 5 apples, they give away 10, and then they get 8 back. So they end up with 3. And if we don't care about those intermediate steps, if we only care at the start they had 5 and at the end they had 3, in the end we could assume at some point they had -5 apples because they lost 10. But really what must have happened is they lost 5, they gained 10, then they lost 7 later or whatever, and they ended up with 3. I'm sure those numbers were wrong there. I did them quite quickly. But there's a time ordering that's happening here. But if you don't care about what's going on in the middle of the system, you only care that they had 5 at the start and they have 3 at the end, then you could have negative states in the middle. And we're used to dealing with that. We're used to dealing with that, for example, in money. So we will say people have minus £800 in the bank. And that just means that whenever they earn some money, the first £800 has to go to the bank. But in reality, nobody can have minus money. It doesn't make any sense. The real system is that you have zero money, and there's an additional condition floating around in the system that says you will not have money above zero until you gain another £801. So you can either calculate the system with this negative number, this negative 800, or you can calculate with zero and a condition sat on top of that that says, look, this person cannot have money above zero until they earn a certain amount. And both of these ways of formulating the system and doing the calculations are equivalent. But in one of them, it looks like somebody has negative money, and they never do. But it's something that we're very happy and comfortable dealing with. You know, if I go to my PayPal account or whatever, it might say that it has a certain negative number in it. And people are quite happy nowadays with that idea. People are very happy with this idea of negative money. And therefore, all he was saying in this paper is that people should be comfortable that if these negative probabilities come out in intermediate steps, like that calculation with money, then we should not be worried about that. We should not be concerned, because by the end, they will disappear anyway. And I think that the killer quote from this paper, if people actually understand it properly, is, it is not my intention here to contend that the final probability of a verifiable physical event can be negative. On the other hand, conditional probabilities and probabilities of imagined intermediary steps, like our person having negative money, may be negative in a calculation of probabilities of physical events or states. So this is exactly what you've been saying all along, is in the mathematics that describes, that we use to get to the probabilities of final states, we can have imaginary numbers, we can have negative numbers, and they can be useful in doing calculations. But by the end, we have to have positive probabilities in the end. And even Feynman, when musing about negative probabilities, is saying, look, these can only come up in intermediate steps, in conditional probabilities in intermediate steps. They can't affect the probabilities of physical events. So they quote that first line and they completely forget that he's totally on board with the idea that you can't have negative probabilities by the end in quantum mechanics. I think the reason so many people are kind of on this is because there is a kind of obsession with the idea that quantum mechanics is some sort of a kind of Wild West, and anything goes in there. You know, we have a whole kind of ecosystem of quantum woo stuff, and it's a confusing probabilistic theory that people aren't used to dealing with, right? People are used to dealing with classical physics, things having definite results. So when we get these systems that have uncertainty, these systems that have probabilistic results, people think there's more room in there and less rules than there are.
Yeah, you see a lot of things, a lot of advertisements where people just put quantum in front of something. Here we had some quantum water purifiers, you know.
Yeah. That's over in India somewhere?
Yeah.
Yeah. It's madness. There's a big quantum woo. There's a big quantum woo kind of ecosystem. Now, what I saw, this is kind of an aside off the negative probability. So we've kind of hammered this to death. I think what we need to take away from this idea of negative probabilities is that these negative probability states can appear in intermediate steps. They can appear in calculations, but by the end, in quantum mechanics, all probabilities are positive. Bottom line. And that's what we need to take away. But I think looking at the discussion that we had, I think a lot of the reason that this is so pervasive as well is because of the kind of way that people, famous physicists like Dirac and particularly Richard Feynman, have had an impact on the public. Why do you think that Feynman has such a massive cult following amongst both physicists and non-physicists? Why is this a guy who kind of everyone has heard the name of, whether they're in physics or outside physics?
Yeah. He's kind of one of those crossover figures from physics.
Exactly.
Kind of crossover into popular imagination. And I think it's at least partly because physicists like him, I think, because he's a physicist who's also kind of like a cool guy, and not people like other people like him because he's a cool guy who's also a physicist.
Yeah.
He seems like, compared to other physicists, he seems like more of like a regular person with regular interests, like playing bongo and so on. So I think to a certain extent, Feynman also, from what I've read about him, cultivated a everyman persona, and he liked hanging out with people outside physics, of people with all sorts of things. So he was very comfortable with it, and he was also like, obviously his physics was amazing, and his chief achievement was formalizing the theory of quantum electrodynamics, for which he was awarded the Nobel Prize with Shinichiro Tomonaga and Julian Schwinger in this picture. But these two gentlemen are not quite as popular Feynman is, and that has to do with his personality, his being an extremely magnetic personality who was also an excellent communicator of science. And you really see the kind of passion he has for science when he does communicate it. He's like very happy to talk about science, and that kind of and because has this whole regular guy thing, I think people really respond to that. And somehow, and I think, of course, it's not a good idea to subscribe to cults of personalities, but at the same time, Feynman had those qualities which kind of attract a lot of people to a cult.
Yeah, I think that's right, and I think it cuts its weight. So I totally agree with you. Obviously, within physics, he had this brilliant track record, right? The kind of the prototype, the first kind of gauge theory dealing with QED with Tomonaga and Schwinger, obviously a massive accomplishment. He was involved with the Manhattan Project as well, so obviously a very important project in just history and wider politics. I also think that Feynman diagrams kind of pervade the popular culture, right? So when you want to draw in a movie something complicated on a blackboard, this is the sort of thing you will see. So you'll see maybe the Schrodinger equation up there written out, and you'll see one of these diagrams, and this almost signifies in kind of layman sense, oh, something really complicated has been put on the board in a simple way for me to see, right? So I think also these pervade the culture as something that shows complexity, and these were brilliant in the sense of the amount of information that is condensed down from massive long integrals in quantum field theory into these tiny diagrams. The amount of information density in these on the physics side is amazing, and then on the layperson side, people even know that there's a hell of a lot going on in here without even seeing. So I think he had those massive impacts. I also think, like you said, he was an excellent teacher. So people talk about the Feynman lectures in physics, which are quite accessible for people who have a little bit of knowledge of physics in quite complicated topics as well. So obviously he had that kind of pedagogical, that teaching aspect as well. And like you said, I think there is a little bit on the other side of this kind of coolness as well. So, like you said, playing the bongos, being a bit of an everyman. And he also has this kind of almost, what's the best way to say it, kind of a bad boy attitude, or a kind of contrarian attitude, with saying, science is the belief of the ignorance in experts and these kind of things, saying basically think for yourself. Now, I think in the modern day, I sometimes see that used in a negative way, as in put up as a poster child for, I see his face on things about flat earth and anti-vax and things like this. So it can go negative the other way as well. But I agree with you. I think a little bit of this everyman rebellious attitude, which some would say went too far the other way. Some people argue he was quite misogynistic and things like this. I don't know. I haven't looked enough into that. But I think some of this kind of everyman and bad boy attitude also kind of works in his favor as well.
I think he had a certain style of doing physics. Both his personality and his physics reflect a certain style, which is no patience with nonsense, like cut through the bullshit, go straight to the heart of the problem, not worrying about what other people, the experts think, and so on, which is pretty attractive to a lot of people, that thinking that rebellious attitude. And it's a unique style that he had,
Yeah.
which also to me, like, we all of us hope to incorporate some of it in our work as well.
Yeah, I agree. And I think that's what I saw on the thread when people were discussing it. It was kind of, like you said, it's like, well, Feynman's got this paper, which obviously people haven't read properly, but then they felt like you were almost attacking Feynman. That's what I felt in some of the discussions. It was like, well, I'm going to trust Richard Feynman, or I'm going to trust Paul Dirac over you. Who the hell are you? And then
Feynman would be the first person to take
exactly. But as we've kind of discussed today, Feynman would be the first person to have agreed with what you were saying. But I think people, because they hadn't potentially fully understood that paper or hadn't read it, I mean, I don't expect everyone to go away and read these papers. It would be nice if they did. But I think people immediately jump and say, well, here's a paper with Richard Feynman saying negative probabilities on it. He's this genius and free thinker that I admire an awful lot. And therefore, people on social media, because that's what exactly. People on social media, nobody thinks sensibly on social media, right? So people, I think, felt like maybe you were attacking this character, and that's where some of the silliness came with this. But obviously a very revered figure in physics and outside physics. Like you say, I think it was a really nice explanation that you said. He's one of these rare crossover figures. If I think about people like Feynman, like Einstein, for example, there's not many of these crossover figures. Stephen Hawking might be another who pervades the popular culture, but he very much was one of these figures. So as we come to the end of this discussion, what do you think the viewer should take away from this discussion of negative probabilities? What are the key messages that they should take from the idea of negative probabilities in quantum mechanics?
I think the first key message is probability in quantum mechanics is never negative. And second is that, in some intermediate steps somewhere, in some steps, you could get quantities that look like negative probabilities, but those are always in the intermediate steps. In the final results from the probability distribution, they always go away. The final results, final probabilities predicted by quantum mechanics, as far as we have observed, is always positive. And third is, it's possible that in the future we will have something like, negative probability densities appearing somewhere in some theory. We should be open to that possibility, as Feynman said. We should try to interpret it in, he gave different possibilities of interpreting that kind of thing. And we should be open to that. But right now, as far as we know, this is it. There are no negative probabilities predicted by quantum mechanics.
And don't take the word of authority figures like whether they be Nassim Taleb, whether they be me and you, whether they be Richard Feynman. Don't take them as gospel. Things can change. Excellent. Good. I wanted to discuss one more thing before you go, by the way. And this was this idea of the Nobel Prize recently in physics. So Nobel Prize 2024, it went to John Hopfield and Geoffrey Hinton for their work on foundational discoveries and inventions that enable machine learning with artificial neural networks. Now, this seemed to get people a little bit upset in our kind of online physics space. I know you asked the question. There was a lot of people saying, well, this is not physics. This is AI. This is computer science. You did a poll which tried to assess this in our little online Twitter X space. And it seemed that most people, the majority of people, seem to think that, nope, this is not physics. Now, any thoughts on this? Because it didn't really bother me too much. What are your thoughts about this?
I'm not very familiar with the work that won the Nobel Prize, and so I don't really have an opinion myself, one way or the other. I try to have opinions on as few things as possible.
Even less things after running into Taleb, yeah.
But the impression that I have is this was definitely physics adjacent, especially Hopfield's work. And, I intend to learn more about it, but it doesn't really bother me. I don't get Nobel debates.
Yeah.
Because for me, the main positive of Nobel Prize is that it brings a lot of public attention to the cool science.
Yeah.
And so as long as it brings public attention to some cool science, I'm cool with it. It's all good as far as I'm concerned. But it was fun to see this level of polarization that people have. So you can see in the poll that a lot of people thought, no, it's not physics.
Yeah.
But then if you also add the people who thought, yes, it's physics, and part of it is physics,
It's basically the same
like
number.
38.4%. It just goes, the poll just goes the other way a little bit.
Yeah.
So very 50-50 polarization, people thinking, and I think this is a fair representation of what physicists think, where they stand. It's kind of very much divided on this. But having said that, for me, I mean, it's just good fun. This poll was just in good fun. I think, it's all good as long as people get excited about some interesting science.
Yeah, I didn't really have any too strong feelings about it. I mean, particle physics, my background is in experimental particle physics. We nowadays rely very, very heavily on AI in triggers and data analysis. So it's at least physics adjacent and something that experimental particle physics couldn't do without. And there's also a lot of fuzziness in the prize boundaries, right? So there isn't a computer science Nobel Prize as far as I'm aware. They're quite restrictive in the fields that they have. So if you have, it's very, very clear that AI and machine learning are becoming very, very important. Where would you put it in? Would it go into sort of mathematics? It's not going to go into chemistry, really, is it? So I don't really have any too strong feelings about it being kind of recognized in physics. I also accept that physics has probably been stealing the chemistry Nobel Prize like over and over and over again over the years. So, there's a lot of slippage between these boundaries, and it
Boundaries
probably
of the
needed
fields are always a little bit fuzzy, so that's
exactly. So, I mean, what I would take away from this is that you probably need a computer science Nobel Prize, right? This is obviously a very important field, a very quickly evolving field, and I think if you had a new prize for that, and I'm sure there are lots of prizes in that field.
Yep.
Sorry, were you going to say something?
No, I'm saying I'm all for a Nobel Prize in computer science. I think that's a good idea.
Yeah.
Maybe some of us can steal those Nobels.
There's just another one we can steal back then, yeah. So, I mean, I do understand on the other side. I am slightly sympathetic to people who are like, well, or at least concerned that AI and machine learning are kind of going to take over every single field, right? So you're going to have AIs writing papers, kind of coming up with new theories, doing all of the experimentation. You don't need any hands-on. So I can understand why people are skeptical, slightly worried, but I really don't think it's that massive a thing. And I think usually the people who get really excited and really complain about this are people who already have some kind of axe to grind. So they're already like, science is in big trouble. We haven't invented anything in theoretical physics for ages. Everything is like it was 50 years ago. Oh, and now they're stealing our Nobel Prize. Like, oh no. Like, I think a lot of the time the people getting really worried about this are people who are already trying to push this idea that there's big problems in physics already. So it's just another way to do that. But I didn't see this as a big problem. Like I say, my big takeaway from this would be just have a computer science Nobel Prize. And, we live in the modern world now where it's very important.
Yep. I think there are a lot of people who, in discussions, there were a lot of names coming up of physicists who could have won the Nobel Prize this year. So it's not that, we have run out of people to give Nobel Prizes. That's absolutely not the case. There's Michael Berry, there's Janendra Jain, there's Charles, there's Peter Shore, a lot of people whom you could, who are contenders for, who deserve to get a Nobel Prize. So it's definitely not the case that physics is in crisis or we have run out of achievements to give Nobel Prize.
Like you say, there's always a lot of subjectivity in these, right? Like, why should this person win it over this person? Like, I think people take it a little bit too seriously and suggest that it's almost an objective stamp of quality or where the field is, when it's just the opinion of a small number of people who to give that prize to. And, other people will have another opinion, and that's totally fine.
Yeah. I mean, taking the prize too seriously is like putting the cart before the horse. It's not, the prize goes to the work. The work is more important. than the recognition.
Yeah.
So
absolutely right. Nirmalya, I've had a lot of fun discussing this. I hope Taleb has now gone away and isn't going to start jumping up in your mentions again.
thanks for having me, Sam.
It's an absolute pleasure.
It was a
So
lot
just
of fun,
before
yeah.
you go,
Sure.
I want to point people to your Twitter first of all.
Oh.
So Nirmalya has a fantastic Twitter where he explains a lot of fundamental physics with some brilliant threads. He's also a science writer and communicator, so he has some fantastic pieces. Particularly enjoyed his piece on J. Robert Oppenheimer and his contributions to physics before the Manhattan Project, because obviously he's very much remembered for his work on the Manhattan Project. But what kind of things did he work on before the fame of the Manhattan Project, Nirmalya? What were his major contributions before that? Maybe people will be interested in hearing that as well.
Yeah, so one of his main contributions, which I wrote about in this article, was proving that black holes can be real. So before Oppenheimer's work, black holes had been found as a solution of Einstein's equations, but everyone thought, these are just some mathematical artifacts.
This is another situation where a mathematical oddity has then...
Yeah.
Okay, good.
Exactly. So people thought, they're not real. And then Oppenheimer's big contribution was he considered like a star which is collapsing, and he asked like what is going to happen to the star which is collapsing, and then he showed that the star collapses into a black hole. So black holes, there are processes by which a black hole can form in nature.
So it's not just an intricacy of the mathematics, it's something that physics could allow to occur.
Absolutely. Before that, people thought black holes cannot form, it's just a mathematical solution of the equations. But he showed no, there is these processes which actually allow you to form black holes. And that makes kind of black holes real. And he should have won a Nobel Prize himself if black holes had been discovered in his lifetime, which did not happen. At the time, there was a lot of skepticism around black holes. But that was a major achievement of Oppenheimer. And, if he hadn't gotten involved in Manhattan Project, who knows what he could have achieved just in physics. But then he went more into the administration side of things, but he was a brilliant physicist before that.
Amazing stuff. So Nirmalya does a lot of this outreach, fantastic threads on physics on Twitter or X, whatever we're calling it now, and some fantastic articles elucidating fundamental physics. So I suggest you head over there. Anywhere else that you'd like to point people to, Nirmalya?
No,
this is the place to find you. This is the place to jump on you like Taleb does and see what you're doing. Good stuff. It's been an absolute pleasure, Nirmalya. What are you up to this evening?
Nothing, just going back to work now.
So back to work. So you get to talk to me and then you get to go back to work. That's fantastic. Well, have a wonderful weekend. It's been great chatting with you, and let's chat again soon, buddy.
Thanks, Sam. The pleasure was mine, and see you soon.
Take care. Take care. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.